Good evening, everyone. Thank you for coming, and welcome to the 2025 Sustainability Changemakers Showcase. A little bit of rebranding from our previous SEDTalks name. So my name is Jeff Brooke-Thorson. I'm the former Associate Director for TISED, which is the Trottier Institute for Sustainability in Engineering and Design. And I'm also a professor in the Department of Mechanical Engineering, where I lead the Alternative Fuels Laboratory. Along with Professor Subhashis Ghoshal, TISED Director, I would like to welcome everyone watching and here for tonight's Sustainability Changemakers Showcase. Before we start, I'd like to acknowledge that McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples. We acknowledge and thank the diverse peoples whose presence marks this territory on which people of the world now gather. For those who don't know much about the SEDTalks program, the initiative was created 10 years ago. This is our 10th SEDTalks event. We created it in order to highlight the excellent research that was being done across the Faculty of Engineering in all aspects related to sustainability in engineering and design. And we wanted to look at topics that were important to transitioning our society towards a sustainable future. The training starts off in the fall with a call to all graduate students in our programs to join into our SEDTalks training program. There they take a set of communication skills building workshops over the course of the fall, and that culminates in our SEDTalks event in December, in which students present their research in 3 minutes. And through those 3-minute theses, we have our SEDTalks winners. And then we select from those presenters our 3 changemakers, and those 3 changemakers are here to present their talks tonight. And over the course of the winter, they've developed their 3-minute talk into a 15-minute presentation that you will hear tonight. So as I said, this is our 10th event. We're really excited to see that we're now a decade old, and that we have graduated a cohort of 27 changemakers plus the 3 who will be presenting tonight. I think for me, one of the most rewarding parts of being involved in SEDTalks over the years is to see that cohort of changemakers go on to do great things in their careers, but also to give back to this community. We had several of them involved as members of our selection committee, of our skills training programs, giving feedback to our changemakers during the winter. Several of them are here in the audience tonight, and I really think it's amazing to see this community build out of this program, and they've really truly risen to the challenge that we aspired to them, which was to become agents of change in our society. And so speaking of past change makers and giving back to the program, it's my pleasure to welcome Fatima Afzal, a former change maker who completed the SEDTalks program in 2023, who is going to be our MC for tonight's event. Fatima.
Thank you, Jeff, for the introduction. I'm Fatima Afzal, a past year changemaker and also a PhD student in the Department of Civil Engineering under the supervision of Professor Dominic Fregon. As an alumnus changemaker with TISED, who has been on the stage 2 years back, I completely understand all the kind of emotions that you guys may be undergoing right now. And being a part of the SEDTalks training program has really helped me view presentations from a different angle, more of enjoying the presentations while I do it, rather than seeing it from a place of fear, and instead see it from a place of more confidence and enjoyment. And over the past 2 years, I have also had the privilege to be on the other side of the training program to support to my mentor, Dr. Andrew Churchill, with the presentations, and helping our new change makers grow and witnessing their transformation has been nothing short of incredible. So tonight, at the Changemaker Showcase, we'll hear from our 2025 Changemaker cohort, Hoda Ahmed, Stephen Walker, and Saadia Wasim. They'll take us on a journey to explore how sustainability can drive innovation, from creating better batteries to producing natural gas and cleaning our water sources. A few words about the format of today's event before we get started. So we have 3 speakers, each of whom will be presenting for about 15 minutes, and we'll be going in the order of one after another without any stop in between. Which means if you have any questions, don't ask in between. We have a separate Q&A session towards the end. And in case if you need to leave during the event, we kindly request you to wait and do so after each presentation is done and do so during the speaker transition period. And a couple of reminders: make sure your phones are on silent mode and don't drink when speakers are presenting. And also, we understand that you would want to take pictures because you have your loved ones here on the stage, the people whom you know. So do it so, but then make sure that you don't stand up and disrupt the flow in between. You can do so by sitting down. So our first changemaker of the evening is Hoda Ahmed, a PhD student in the Department of Mining and Material Engineering, working under the supervision of Professor Jinhyuk Lee. With Hoda, let's take the journey to find out how salt can help us create sustainable batteries.
There are three big problems with the battery you see in this car. It doesn't have enough range. So if you want to drive further than Quebec City, you might wish you had a gas car. Also, it's really expensive. Not everyone can afford it. And I believe that most of you guys know that this car is not green. Yes, because the battery in this car is not green. It's full of toxic chemicals. So today, in the next 10 minutes, I'm going to teach you how, with my research, I try to solve most of these issues. But I think now everybody curious about lithium-ion batteries. Let me first explain to you what is lithium-ion battery. Lithium-ion battery consists of two main electrodes, anode and cathode. Lithium ions move back and forth between these two electrodes through the electrolyte. When we initially build lithium-ion battery, we build it in a dead form or in a discharged form. Why? Because all the lithium ions are in the cathode structure. Once we started charging it, we forced lithium ions and the electrons to move from cathode to anode. Now we have our battery fully charged. Once we started driving our car or using our phones, lithium ions and electrons will spontaneously move back to their original structure, which is the cathode part. So this lithium ion movement back and forth between cathode and anode determine how much energy you can store in your battery. As you can see, there are several components in the lithium-ion battery. Among all these components, I choose to work in cathode material. Why? Because the cathode material is the most expensive and heaviest component in the battery, which means it is the component that determine or that has the most influence on the battery cost and energy density. So there are several kinds of this cathode material, most of them made of cobalt and nickel. Let me show you one of the most commercialized cathode material. This cathode material has layered structure. And for simplicity, I'm just giving you here a simple example, which is lithium cobalt oxide. In the layered material, lithium and transition metal, which is cobalt here in our case, are arranged in alternating layers, which means we have lithium, cobalt, and so on. With this layered material, we can get around 600 watt-hour per kilogram energy density. And watt-hour per kilogram is how we measure the energy density. And this material will be our reference point for today's presentation, which means I will compare my material performance later with this material. So now let me introduce to you the material that I choose to work with. This material, or the material that I choose to work with, has more lithium in the structure. Also, it can be made of manganese instead of cobalt. And unlike the layered material, this material, or the lithium ion and manganese in this material, can be made of or it's randomly distributed in the structure, as you can see in this image. So let me tell you the name of this material. This material called lithium-rich disorder rock salt cathode material. I know the name is too long, but the good news is you can just call it DRX. So the question now is, why I choose to work with this specific cathode material? Why I choose to work with DRX? Simply because this material, or with this material, we can get around 1,000 watt-hour per kilogram energy density, which is very high compared to the commercialized one. You might wonder, why, if this material is very good and can get this high energy density, why it's not in our battery yet? Simply because this high energy density doesn't last forever. It declines so quickly, as you can see with the red line. So in my PhD, I'm trying to solve this issue. I'm trying to make this red line as flat as possible. Or you can say that I'm trying to make the energy density of the DRX material as stable as possible so we can take advantage of this promising material. Let me explain to you how did I do that. First, I tried to understand why this material or why the energy density of this material declined quickly. I looked into the literature and I found that the main issue with this material is the synthesis method that people use to make it. When people try to make DRX, usually they mix solid precursor. And because the reaction is between solid-solid, it needs high temperature like 1000 C and long time like 12 hours in order to be synthesized. And because of this high temperature and long synthesis time, this led to a very large particle formation. The issue with this large particle is that it will take forever to extract lithium ions out of this structure, especially the one in the bulk. People solve this issue by a simple means. They just crush this large particle into smaller ones. But as you can see, this small particle, most of them has non-uniform morphology. And there is a big issue with this non-uniform morphology nanoparticles. The issue with this particle is that as long as we use it to make the electrode film that we use to make the battery, this non-uniform morphology particle tend to cluster or agglomerate in a specific region of the electrode film. So now we have non-uniform particle distribution in the electrode film. And as you know that when we charge and discharge battery, we extract lithium in and out of the cathode structure. And this will lead to volume change. And because of the non-uniform particle distribution in the electrode film, this will lead to non-uniform volume expansion and contraction during discharging and charging of the battery. And this non-uniform volume change across the electrode film led to the cracks formation. So now we kind of understand what is the reason behind this fast energy loss of the DRX material. Simply, it is the particle size and morphology. So we thought, what if we can solve this issue? What if we can just make the particle as small as possible from the beginning with a uniform morphology? And we did so. Let me teach you, or let me tell you, how did I do that? When we looked into the literature, we found an interesting synthesis method. This method called molten salt synthesis. People usually use this method to synthesize a very large single crystal. We modified this method to make it able to synthesize a very small single crystal. And this happened by applying two simple steps. Let me explain these steps to you. In the beginning, before we start, we just mixed the solid precursor with a salt, like table salt. And we will understand soon what is the function of the salt in this process. So after mixing the solid precursor with the salt, we heat the mixture slightly above the melting point of the salt. So now we are above the melting point of the salt. The salt will melt and act as a liquid medium. Now the solid precursor, you remember the solid precursor, now it will start dissolving in this molten salt. So we transform the solid-solid reaction to liquid-liquid reaction. Everything now is ions, and this will speed up the reaction. Therefore, we were able to reduce the reaction synthesis temperature from 1000 C to 800 C. Also, we were able to reduce the reaction time from 12 hours to 1 minute. So after 1 minute, we immediately stop the reaction by cooling down the furnace. After this first step, we got like our pure DRX product. But remember, we still have the salt. So now the salt is solidified surrounding each particle. Imagine we have a spherical particle surrounded with a membrane or a solidified salt. But when we checked the image of this particle, we found that there is some non-uniform distribution of the element. And it's obvious because we already used like low synthesis temperature and time. That's why we applied a second heating step. In this step, we heat the mixture or the product of the first step, the one with the single particle surrounded with the solidified salt. But this time we heat it below the melting point of the salt. Why? Because of two reasons. If we heat the mixture in the second step above the melting point of the salt, that means the salt will melt and the reaction will proceed. So the particle will get bigger and bigger, and we want to avoid this. That's why we heat the mixture below the melting point of the salt. And the second reason is that because now we have the single particle surrounded with the solidified salt, we want to take advantage of this solidified salt. Therefore, this solidified salt will act as a physical barrier, which will prevent any further contact between the particle, and this will prevent any further particle growth. So now, by applying these two steps, we obtained, or we were able to transfer all this non-uniform particle to a uniform particle, as you can see in this image. So now we have a nanoparticle or a single crystal nanoparticle. Now we have the material ready to go. But remember, we still have the salt. You remember I told you we have the single particle surrounded with a solidified salt? So now we have the particle still surrounded with the solidified salt. We cannot use this in our battery. So we need first to remove the salt. We did simply by washing the material in water. So after this washing step, now we have our single crystal nanoparticle ready to go. Now we really can use the material. But anyone curious before I move on to see the real image of this particle? Okay, here's our beautiful manganese DRX single crystal particle with a particle size less than 200 nanometer. And as Professor Jeff said, it looks like a marshmallow, but we are not gonna eat it. We will just use it to make a good battery. So indeed, and with this nice looking morphology manganese DRX material, we were confident that we will get a very nice performance. Indeed, when we used this particle to make the electrode film, we achieved a nice particle distribution, as you can see in the electrode film, unlike the one that used the crushed particle. With this nice particle distribution, we made the battery, or we built the battery, and we got this performance. Unfortunately, the performance was terrible. It was a huge shock for us. As you can see, the performance is like the blue line one. So we started thinking, what did we do wrong? We revised every single step in our method. Finally, we figured it out. Do you remember when I told you that we need to wash the material to remove the salt? That's when the problem happened. We didn't just only remove the salt. We also removed the lithium from the structure. So now we don't have lithium in the structure. That's why we don't have energy. We started thinking again. How can we solve this problem? We thought we need first to understand why lithium left the structure in the first place. And we understood this. Let me explain to you. Lithium left the structure because the lithium concentration in the structure is very much higher than lithium concentration in water. Water doesn't have any lithium. Therefore, this made like a concentration gradient. Lithium concentration in the structure is higher, so lithium just jumped into water to reach to the equilibrium. And this helped us to solve the problem. We thought that, what if we can just reverse this process? And indeed, instead of applying a second step and washing the material in pure water, what we did is that we washed the material again, but this time in a highly concentrated lithium hydroxide solution. So we wash the material with a highly concentrated lithium solution in order to let lithium leave the solution and jump back into the structure. And this is what happened. And when we test the performance, or when we test the material, we found that indeed we got our lithium back. So now we have our marshmallow particles with our lithium back in the structure. The material is ready to go. Now let me show you the performance of the material. Oh, it's not this one. This was the terrible one. This is the real performance. As you can see with the blue line, with our synthesis method, we were able to obtain a stable 600 watt-hour per kilogram. It's still not 1,000 watt-hour per kilogram, but at least our material is comparable to the commercialized material or the layered material that has been extensively studied for decades. Also, a good news, my colleagues and I trying to make the particle even smaller and trying to improve the lithium diffusion in the DRX material in order to be able to reach it to a stable 1,000 watt-hour per kilogram. So far, I was talking about the energy density or the range. And I told you that we are working to make a stable 1,000 watt-hour per kilogram energy density. What about the cost and environmental impact? I didn't talk about it, right? Actually, I did. Do you remember when I told you that my material, the cathode material that I'm using, can be made of manganese instead of cobalt? That's when I talked about the range and environmental impact. Because cobalt is 14 times more expensive than manganese. And it's not only about the price. Cobalt mining is linked to unethical practices and environmental harm, while manganese is more safer option and cleaner option. So by using manganese, we are not just turning our lithium, or we are not just making our lithium-ion batteries cheaper, but we are making it more cleaner and more sustainable. And this is the best option for our future. Thank you.
Thank you, Hoda. On the stage next, we have our change maker, Stephen Walker, a PhD student in the Department of Chemical Engineering, working under the supervision of Professor Sylviane Coulomb and Professor Jan Kopesinski. Tonight, with Stephen, let's unravel the process of making natural gas out of thin air.
In 2015, McGill calculated the amount of CO2 emissions it produced in a year, and it was 54,000 tons. The surprising part, 64% of McGill's emissions comes from natural gas. When I saw this, I was shocked, but I soon figured out it's because McGill has 3 natural gas boilers that it uses to produce heat for almost all the buildings on campus. The good news is in 2024, McGill spent $30 million in order to replace one of the 3 natural gas boilers with an electric one. The only issue is that even if McGill has the money to replace the other 2, they can't because our electrical grid can't actually handle the electric load. So let's take a pause here. What happens if McGill doesn't actually have to change its natural gas infrastructure? What happens instead? It can change the way we produce natural gas. So let's take a look. Currently, it's the opposite side. Currently, we take carbon, natural gas, or carbon currently sequestered in the ground, and we take it and we burn it, and we produce heat to heat our buildings and carbon dioxide. And we do this over and over and over again. And so what we do is we just keep on taking more sequestered carbon and keep putting more carbon dioxide in our air. But what happens if we didn't have to do this? What happens if we can take the carbon dioxide we currently already have in the air, because I've been told we have a lot, and we can take that and we can keep the carbon we currently have in the ground and just use this. How? Well, we can use direct air capturing, take the CO2, and what we can do is we can react the CO2 with hydrogen, which we produce by green energy, by taking a water molecule and splitting it into hydrogen and oxygen. And from this, we can produce methane. If we do it this way, we could potentially take this methane, put it into our current natural gas infrastructure, and without having to take any more of the sequestered carbon out of the ground. My name's Steven, and this is the problem I'm trying to solve. So, what is this reaction? Well, we take green hydrogen, we take CO2, and then we produce methane and 2 water molecules. And the great thing about this reaction is that we can produce this reaction at 300 to 400 Celsius, even at atmospheric pressure. And we're doing this right now at McGill. This is my reactor. The way it works is CO2 and hydrogen flow this side across the reactor bed and produce methane. Our reactor usually works between 300 and 400 Celsius, and we can raise the pressure from 1 to 10 atmosphere. Now, how do we measure conversion? Well, we use a mass spectrometer, and we can calculate the total amount of CO2 that's converted. If you see that dotted line at the top, that is the thermodynamic equilibrium for the amount of CO2 conversion we can produce. What this means, looking at the graph, is that the lower the temperature, the more of the CO2 we can convert. Now, for the rest of my talk, any data I show you will be done between 300 and 400 Celsius and at 2 atmosphere. And now I want to bring your attention to the most important part of the catalyst, of the reactor, the catalyst. Now, in order for CO2 methanation to work at this temperature, we need a material that can increase the reaction rate. We call this a catalyst. And in our case, I am using a nickel catalyst. The reason is, it's actually fairly cheap. Its downside is it unfortunately takes a higher weight percentage, and also it usually reacts at a higher temperature. However, due to the cost benefits, it's the catalyst I decided to use. Now, what we want to do is we want to increase the conversion of our catalyst. And one way we do that is by adding a support. The reason is we want to increase the surface area of the catalyst. And what the support can do is it can help anchor the catalyst into smaller particles. The smaller the particles, the higher the conversion. The way to see this is you can just put more CO2 active sites on the surface. Now, there's a couple other ways we can increase the conversion of our catalyst. One of them is we can take the support and we can increase its surface area. This way, we literally have more spots to put our small nickel particles. The other way, and sometimes the support can actually help speed up the reaction with the catalyst. So your reaction speed, hence your conversion, is actually faster with a support and catalyst than the catalyst alone. So currently, most catalysts use an aluminum, but there's been a new catalyst that's came out. It's carbon-based. And starting with a graphene sheet, this is pretty much just a 2D structure of graphene atoms. You can roll it up into a tube. Now this is called a carbon nanotube. And to give you some context, it's about 1,000 times smaller than a Twizzler, to give you a size comparison. Now, why would you use this carbon nanotube? Well, they have great surface area, and also this tubular structure helps form small nanoparticles, which we like. Also, the great part is shown in the literature that the carbon nanotubes themselves can actually assist the catalyst with electron transfer, increasing conversion. However, for our catalyst, nickel, there's one slight problem. Oh, I forgot to mention, one of the things I love about this catalyst is it looks like my favorite candy, It's called the nerd rope. And it's where you take a Twizzler and nerds and you put them together. This will be relevant later on. Now, going back to the carbon nanotube. So carbon nanotubes are actually stable for CO2 methanation. Their temperature range usually caps out around 400 Celsius. But there's a slight problem. Nickel particles like to be formed and reduced at above 500 Celsius. So the problem is carbon nanotubes can be damaged forming nickel particles on their surface. Now, one of the potential solutions is to use a material like carbon nanotubes, which means it has the same tubular structure we want and has the same similar surface area. However, this material is thermally stable over 900 Celsius in air, and it's called boron nitride nanotubes. Now, what's the difference between a carbon nanotube and a boron nitride nanotube? Well, it's based on their atomic structure. So we know a carbon nanotube, geez, I'm getting this all, it's my left and right. It's a carbon nanotube, it is a tubular structure of carbon atoms. Well, a boron nitride nanotube, it's a tubular structure of boron and nitride atoms. The way I like to think of the difference between a carbon nanotube and a boron nitride nanotube is a boron nitride nanotube is simply a different flavor of Twizzler. Now, why boron nitride nanotubes? Well, I spent 4 years working at the Canada National Research Council, working with my research group on boron nitride nanotube purification. There, we were able to take our purity of boron nitride nanotubes from 40 to 50%, all the way to 84% using a chlorine gas treatment, 950 Celsius. What we ended up with, if you see the Twizzler, compared to the Twizzler, it's more like a red licorice string in that all the roughness has been taken out, and we now have this very smooth nanotube. One of the things I thought about is once I got this material is there must be some environmental sustainability applications for this material. And luckily, I had 2 supervisors. One of them wanted to do CO2 methanation, and the other one wanted to do ammonia synthesis here at McGill. However, they were looking for someone who had expertise in boron nitride nanotubes. So they hired me. Now, the first thing I needed to do is I have my nice purified boron nitride nanotubes. I had to make sure that I could get the nickel nanoparticles onto the boron nitride nanotubes. And using an electron microscope, we were able to drop cast some of our nickel precursor, nickel acetate, and start raising the temperature. And as we raised the temperatures, we could see particles forming on the surface. And when you take a close look, they look exactly like a nerds on a Twizzler. After this, I used the reactor I showed you before. For the activities test to check their conversion of CO2. However, before I show you the nickel catalyst, I was so excited and so confident this worked. I actually tried the boron nitride nanotubes first without a catalyst because I was confident it would at least be somewhat catalytically active, so it would be able to help the nickel catalysts with the reaction. However, that was not the case. It was almost zero. Luckily for me, when I tested the nerds rope, I was able to get a conversion at 52% at 400 Celsius. However, this was still well below the thermodynamic equilibrium and what I was aiming for. Ideally, I would have a catalyst between 70 and 90% conversion. So what went wrong? And this is something I've actually thought long and hard about. And I realized it was probably due to the purity of the boron nitride nanotube. It turns out it probably was too pure. The issue is, I want you to take a good look at the Twizzler. Oh, perfect, I'm on the right side for once. And you can see that there's a certain roughness to the surface and there's some grooves. The surface roughness does 2 things. It helps anchor the nickel particles better on the surface so they're more stable. And secondly, it's the surface roughness the CO2 can potentially react with for the support material for the boron nitride nanotubes to assist with the CO2 methanation reaction. So what my current plan is actually undo all 4 years of my hard work at the National Research Council of Canada and use a lower purity boron nitrate nanotube for my next round of experiments. However, and I am confident this material will at least be higher in catalytic conversion. And I hope to also, using this new catalyst, test the material for ammonia synthesis. This is where boron nitrate nanotubes really shine, as ammonia synthesis happens in a lot harsher environments, which boron nitrate nanotubes are perfectly suited to. The interesting part about the ammonia synthesis reaction is that 80% of the CO2 emissions from this process is due to the hydrogen. That's because currently the way we source our hydrogen for the ammonia process is usually through natural gas. Now, I know this sounds like a little bit of a tangent, but I wanted to emphasize that the natural gas, the carbon dioxide emissions from natural gas are a lot bigger than the 2 natural gas boilers we have here at McGill. It's a Canada-wide issue. 13% of Canada's total greenhouse gas emissions, about 88 megatons of CO2 a year, is produced by natural gas used for heating houses. To put that in perspective, McGill in 2015, the amount of natural gas they produced was 0.03 megatons. In 2022, the total amount of Canada's carbon footprint caused by natural gas was 23%, or 160 megatons of natural gas. What I'm proposing here is that we might be able to stop taking our methane from the ground, and instead we can stop sourcing our carbon from the ground, instead source our carbon dioxide from the air, reacting it with green hydrogen to produce natural gas in a way that is a green circular fuel. This way, we don't have to shoulder the infrastructure costs of building, for example, two electric natural gas boilers, and also we can use the current natural gas infrastructure to transport methane. I'm hoping that this talk will act as a catalyst to spark different ways we can approach different ways to approach a sustainable transition to carbon neutrality. Thank you.
Thank you, Stephen. Final speaker tonight is our changemaker, Saadia Wasim, a PhD student in the Department of Civil Engineering, working under the supervision of Professor Stephanie Loeb. Saadia is going to tell us the story of how rays of sunshine can be the hope to clean our drinking water sources.
Water is essential for life. Personally, I like to look at water differently. Or should I say, I like to taste every sip I consume, feeling how heavy or light it is to my throat. 9 weeks ago, when I was breaking my fast with some dates and water, as I was drinking the water, I recalled this newspaper interview which I had read around my high school days. It was about a couple who were traveling through the desert and had exhausted all their water supplies. So basically, they were thirsty and tired. Luckily, they found a house and went for some help. The owners of the house, just like any other Bedouins, served them with some dates and water. That water was a memorable one for them. They clearly remembered how drinking that water made them feel. And so, 4 decades later, when they were being interviewed by that local newspaper, they narrated this water story. I completely resonated with these couples when I was drinking that water while breaking my fast. Also, it would be nice if this could happen today in today's world, like people would travel in resource-limited regions and be served water which they could drink, not fearing how bad it is or good it is. The unfortunate reality is our water bodies today have been contaminated with toxic chemicals, and microorganisms. Fortunately, these toxic chemicals and microorganisms get removed by these large-scale water treatment facilities in developed or urban regions. And thanks to these large-scale water treatment facilities, 6 billion people globally have access to safe and clean water supplies. But knowing that the global population is 8 billion, there are still 2 billion people who lack access to safe and clean water. These 2 billion people live in regions marked by yellow and orange. So now the good question is, how do we help these remaining 2 billion people or these regions gain access to safe and clean water supplies? Those large-scale water treatment plants is not a sustainable option for these regions as they lack those resources. A closer look into these regions shows us that they are located near equator, which means they have sunlight or solar energy all year round. We can use this as an alternate source of energy. Moreover, people in these regions live in small communities like these, and so an ideal solution would be more of a small-scale decentralized unit. Again, in developed regions, water gets treated, that is, chemical contaminants are removed from water using filtration process, which can be energy intensive, and microorganisms are killed or disinfection is carried out using processes like chlorination, UV disinfection, ozonation, and so on. And these have their own drawbacks. I propose the use of sunlight-driven process or solar-driven process for these resource-limited regions. By using sunlight, I don't mean to produce electricity, but to use them directly to degrade contaminants and kill microorganisms in water. Now you may be wondering, how would that really happen? Well, if we use nanoparticles called photocatalysts. So photocatalysts are nanoparticles that have the special ability of getting activated by light energy to degrade contaminants and kill microorganisms in water. To elaborate more, these photocatalysts have a conduction band and a valence band, and once a photon of sufficient energy is absorbed by these photocatalysts, electrons get excited from the valence band into the conduction band. These excited electrons in holes or positive charge then move on to the surface to perform surface reaction. During this process, they generate these short-lived chemical species which have the super ability to degrade contaminants and kill microorganisms in water, breaking them down into safer byproducts. The photocatalyst of my interest is traditionally used using UV light sources, but I want to use sunlight, and they don't really work that well under sunlight. Why? Well, because sunlight contains less than 4% of UV region, which only gets absorbed by these photocatalysts. Here's a sunlight spectrum that reaches the Earth's surface, that is the sunlight that reaches the Earth's surface. On the x-axis, we have wavelength, which you can think of as different regions in the sunlight that reaches the Earth's surface. That is UV, ultraviolet, visible, that is visible to our eyes, and infrared, IR. So these three regions are found on the Earth's surface. On the y-axis, we have intensity, that is how intense is light in each of these regions. So on the extreme left, you can clearly see that UV has the shortest or the smallest portion and the lowest intensity amongst the three regions. And that makes sense why these photocatalysts don't really work that well under sunlight. So the challenge for me was to improve their performance under sunlight. And I approached that by using another nanoparticle called plasmonic nanoparticles. I would like to call them as light antenna nanoparticles for this presentation. These light antenna nanoparticles have this special ability to concentrate light energy on their surface, and this kind of a phenomena does not happen for a photocatalyst. So the thought was, what would happen if we couple these two nanoparticles together? So for demonstration purpose, light rays would concentrate on the surface of the plasmonic or the light antenna nanoparticles, and this would happen for each of the light antenna nanoparticles. This concentrated light energy would then be transferred to the photocatalyst and then help it improve its performance. The light antenna nanoparticles of my interest is aluminum nanoparticles. These were synthesized using a special fume hood setup called Schlenk line. In order for the reaction to begin, the reactor was first placed under inert vacuum followed by an inert environment. Once the reactor was in inert environment, chemicals were added to start the reaction and eventually wind up the reaction. Once the reaction was complete, these nanoparticles were washed and analyzed to check if we have synthesized the desired nanoparticles. Here's the analysis results. You see an image which shows nanoparticles, small balls with two different colors. The core is red, which is aluminum, and there's a thin sheet of oxygen, which is the oxide shell, and this is what I wanted. So this confirms the successful synthesis of my aluminum nanoparticles. Now that I had my aluminum nanoparticles ready, the next step was to attach them or couple them with the photocatalyst. I thought to myself, why not place the photocatalyst in the reactor itself and let the aluminum nanoparticles deposit on top of it, which is an option. But that was not the best thought. That resulted in over-deposition or aggregation of aluminum nanoparticles around the surface of the photocatalyst. This decreased the performance of the photocatalyst, which is not what we wanted. So the only way to overcome this challenge for me was to synthesize the aluminum nanoparticles separately and then attach them to the photocatalyst in a controlled manner. And to do that, I use something called ligands. You can think of ligands as a network between two nodes. So I used different types of ligands with two different attaching groups. That is represented by squares and circles. So I had square and circle, 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 and square. I found that the one with the square and circle performed the best. Next, I thought to myself, if I keep the attachment group constant, what would happen if I vary the length of these ligands? And I found that the shortest one performed the best. So this was a constant for the next round of experiments. And now the big moment. The results for the degradation of a selected contaminant under sunlight using those nanoparticles. On the y-axis, we have percentage of degradation, and it's supposed to increase from left to right. And on the x-axis, we have the time needed for these contaminants to degrade. So first off, we have a control, which is the photocatalyst, and here's how the degradation curve looks like. Next, we have another control, which is the ligand with the photocatalyst, and that's another control. So this is how the degradation curve looks like. In this, we see that these ligands did not impact the degradation performance. That is, it did not increase or decrease the degradation performance. And finally, the hero of my project, the light antenna ligand and the photocatalyst. Here's the degradation curve. We clearly see an enhancement in the degradation performance, and this is about 60%. This can solely be attributed to these light antenna nanoparticles, meaning that these light antenna nanoparticles were successful in concentrating the light energy and then transferring it to the photocatalyst. This was a test run performed for 20 minutes. Now I'm trying to see how long would it take me to degrade these contaminants completely. Another important question that I'm trying to answer is this enhancement because we are absorbing more of UV light or we are absorbing more than UV light? Either ways, with such an enhanced performance, these photocatalysts or these nanoparticles can be coated on sunlight transparent substrates, which can then be used in these solar-powered small-scale water purification systems. So what happens is light penetrates through the sunlight transparent substrate, activates the particles. These particles can then go on to degrade contaminants and kill microorganisms in the water flowing through the channels below the substrate. These solar-powered water purification systems can be used in those communities that have sunlight throughout the year. I too come from a country that has sunlight throughout the year. Summer mornings can be as hot as 45 degrees Celsius, and that is really, really, really hot. You can crack an egg and cook it on the floor. When I started my PhD here at McGill, I was drawn to the concept of using light for water treatment. Maybe because sunlight was a crucial part of my life. But little did I know that sunlight would actually become the theme of my thesis. The results that I presented today were an accidental exploration. They were not the main experiments I was conducting. While I was doing my main experiments, I thought to myself, why not use the solar simulator, which is basically a light source that mimics the sunlight that reaches the Earth's surface? The results we got were interestingly amazing, just like what we saw today. When I talk about my own work, I feel incredibly blessed that I'm able to share my appreciation for both light and water with you today. And most importantly, bring water to a part of the world that is hesitant about it. Hopefully, with this kind of a system, we'll be able to provide safe and clean water to the remaining 2 billion people Thank you.
Thank you, Saadia. I now invite all the three changemakers to be on the stage. We can take a few questions. So we have a volunteer with a microphone. So if you have any question, just raise your hand and we'll have the volunteer come over to you with the microphone so that we can all hear the question. And also when you're asking the question, please to indicate as to which changemaker the question is directed to.
Okay, we're ready. Questions?
Thanks. So good evening. Thanks a lot for all your presentations. Extremely interesting topics today. So this first question would be for the sodium or the salt-based batteries. I was wondering, so we're talking a lot about like the temperatures at which we're applying for these materials to mix and whatnot, but is there any other like physical properties or types of processes that need to be applied? We're talking about mixing, stuff like that. And also, are we considering the state in which that water or that like lithium, rich water or solvent would be coming out of the process? How do we need to treat that? What are the impacts of this like output of the process on the environment? On the environment?
Thank you for your question. So if I understood you correctly, so you are asking if we have any, during mixing, instead of heating the material, we can use another synthesis method to mix?
Are you just heating or are you also mixing and applying other types of processes?
So in the beginning, we mix the precursor, initially mix them in the ball milling, like machine called ball milling, just mix them, the precursor. Then we took to make sure that everything is homogeneously mixed. Then we apply the heating, like take amount of this precursor and heat the mixture. Yeah, and your second question is about washing step. So you are asking if how we get rid of water then after we finish the washing?
Like that output product, is there any impacts of it? Like is it tough to bring it back to the state in which it's necessary to begin the washing? Can be used as is? Like what are the implications there?
Okay, so initially we wash the material in water to remove the salt. Then we dry, we wash the material to remove the salt. Then we wash the material again in lithium hydroxide solution. And we are trying to, after these two steps, we are drying the mixture in a vacuum oven at 1800 C to make sure that all the water just left the structure. Of course, lithium hydroxide has some bad effect on the performance, kind of. If you have excess lithium hydroxide in the material, this might interact with the electrolyte. So of course, finding another way to wash the material to do reinsertion or whatever we call it, reinsertion step, we can look for this one. But so far, it's we are trying to wash with the least amount of lithium hydroxide just to put lithium back. Yeah, is this answer? Okay, thank you.
Nice talk, Jan from Chemical Engineering. Question for Saadia regarding the clean water with photo power. The first thing is, what kind of contaminants did you actually degrade? Maybe you mentioned it, or I was falling asleep, or maybe you did not mention it. And the second thing, maybe you kind of answered this in your last slide, how you prevent that all your nanoparticles actually end up in the water, so that the people don't drink your nanoparticles.
Yeah, so I didn't mention the contaminant. The contaminant that I used was an anionic dye, which is a carcinogenic dye. And the second one would be these nanoparticles will be coated or immobilized on these sunlight transparent substrate. And that would, it's not a slurry reactor, it's like an immobilized nanoparticle onto the substrate. So that would not leach into the water. And if it does, then we can have a filtration system right after this systems to prevent it from reaching into the drinking water.
Hi, thank you so much for your presentations today. To follow up on what my colleague just mentioned, have you given any thought about the sourcing of these titanium dioxide and other nanoparticles that you'll be using, and how we could actually bring these substrates in the regions you mentioned?
If I understand your question correctly, you are asking how would we make these nanoparticles and bring them
Are they affordable? Can we, how are we going to implement the solution, which seems to very, very useful. I'm just curious about how to implement it on the ground.
Thank you for the question. So we are not synthesizing the the titanium dioxide. We are synthesizing the aluminum nanoparticles. These titanium dioxide nanoparticles are readily available. We are buying them from the suppliers for testing them in laboratory settings. They can be fabricated, and I'm using a very small quantity or concentration of these nanoparticles for testing in my reactor, the batch reactor setup. So I believe if we scale up, we can definitely think about what concentration is needed to coat those sunlight transparent substrates, and from there we can definitely go and see what is the next step needed in the design process.
Perfect, thank you.
Hi, thanks for the presentations. My question is about the batteries. I'm curious, so manganese is a critical mineral as well, so a goal in sustainability oriented projects, I guess, is to reduce our use of those materials at all. Is there a reason that manganese specifically is better suited than cobalt, and could manganese also be replaced with another less critical mineral?
Thank you for question. So you mean if we can make lithium-ion batteries without manganese and cobalt and...
Like replace the metal with a less critical mineral that reduces the environmental impact?
I think as long as I know, I think we need some transition metal with lithium. I know that there is like sodium-ion batteries and there are like zinc batteries and lithium metal batteries. But I believe that we still need like transition metal. Maybe in the future we can find something like without anything. I don't know. Yeah.
Okay.
Thank you for the presentation. My question is for Stephen. When you mentioned that you reduced the purity of the boron nitride nanotubes, what impact did it make on the thermodynamic equilibrium or the yield percentage of the conversion of the carbon dioxide to the natural gas?
So that's where I am. So I don't have the data for you yet, and so I can't give you an actual number. However, I do have some preliminary data that when I looked back at my data made me think this. So before we did CO2 methanation, we tested actually two types of boron nitride nanotubes. One was purified at 950 Celsius under chlorine gas, and the other one was purified at 750 Celsius under chlorine gas. What was the surprising is that the 750 Celsius material actually had a higher hydrogen uptake, which means when we were testing the material, it was about, I would say, about 15% higher. It means that the lower purity boron nitride nanotubes actually had more spots for hydrogen to interact on the surface than the 950 material. However, we were testing multiple metals at the time, and so based on the other metals performing better, and also this kind of bias I had that higher purity BNTs would be better, I kind of just, you know, I was like, oh, that's probably like a fluke, or, you know, maybe it's the accuracy of our machine. So I just assumed this is better, but then once I found this out, and once I figured out what has happened is that the material needed defect sites, I realized that the chlorine purification process was purifying the BNTs by actually going through the defect sites. So what we ended up with what at the end of the 950 material is actually very high, very crystalline BNNTs, and any other BNNT that had defect sites would have had been pretty much etched away.
Yeah, thanks for the talks, everyone. And I guess just briefly, you kind of explained, and we see, you know, the obvious longer-term uses and everything. But I guess just in the short term, what would be each of your, you know, briefly your next steps that you're doing here? There's some encouraging results or some encouraging directions, but what would be that next step? Whether it's another round of testing or whatnot. But yeah, for each of you, please.
Yeah, so I'll start. For me, it's just would be remaking the nickel catalysts I showed, but using this lower purified material and testing it in the catalytic plate reactor to see if my hypothesis that the lower purity boron nitride nanotubes would have higher CO2 conversion is actually correct.
My next step I mentioned in my presentation, I will be testing or checking which part of the sunlight is actually causing this enhanced performance. And apart from that, the next plan is to test for the disinfection of viruses to complete the overall picture. So.
As the next step for me is like, and we are trying in our group to make the particle smaller. My colleague Pablo, he's working on this project. And for my second project, I'm trying to make the lithium diffusion inside the particle itself much easier. So even with the large particle, we can still like get the energy, enough energy out of the material. So yeah.
Thanks.
We can probably take one last question.
Thank you. Thank you. I have a question for Saadia. It's a very short-term question. I do work in the Sahel. In certain area, you get a precipitation of about 50 millimeters for a few days, and the water accumulates in areas they call Bahid. So it's very little, but a little water. Now, that water, how would you purify it? We thought definitely that your idea of using the sun will be very important, but the water is already with a lot of dust, all kinds of garbage, you know. So do you have any suggestions?
Well, it would go through a series of processes, just like what I showed in my presentation. If it's got all these dusts and dirt, and definitely it's got contaminants and microorganisms if it has been sitting there for long, then to purify that, it will go through the whole process of a treatment plant, basically. You need to perform filtration, you need to check for the disinfection, and yeah, all of that. You need to perform all of those stuff.
Okay. Do you have the cost for that? Like per cubic meter or something?
That would be hard to answer.
Okay.
Because if water is just sitting over there in a puddle, it's supposed to go down the river for that to be treated, or it's supposed to go through the wastewater treatment plant, or it's supposed to be pumped into the water treatment plant for it to be treated. So I cannot really say how much of water treatment for a small puddle of water would be.
All right. Thank you.
Thank you. Thank you for the audience for your questions, and thanks to all our change makers. Let's give them a huge round of applause. With that, you can go back to your seats, and I now invite Jeff back on the stage for the closing remarks.
Thank you very much, Fatima. And I'd like to thank all of our SEDTalks Changemakers for their presentations, of course, and also for all their efforts over the past 5 months. It's always a long, difficult journey, but we wish you all the best as you carry on inside of your projects. And on behalf of the Changemakers, I'd like to give really a sincere thanks to their supervisors for supporting them in this initiative and giving them the time and space to develop their skills over this time. On behalf of the whole SEDTalks team and the Changemakers, I'd really like to extend a special thanks to all of those who have given their time and feedback to the students over these past months. That includes our past alumni Changemakers, especially Fatima, the members of the SEDTalks committee, with Professors Ali Sifat Koldani and Sydney Omalon, as well as our industrial partners, Avram Goldman and Michael Johnson. Thanks to the whole TISED team for all their work in organizing this event, and especially Dr. Andrew Churchill, whose involvement in this program really is what makes it all possible. You know, this event is just a little snapshot of, I think, of the amazing research that's going on across the whole Faculty of Engineering and really across McGill as a community. And so I hope that tonight these talks have inspired you, the researchers, the graduate students in the crowd, to consider to join this program, to share your research and to share your journey with our colleagues and with the outside world. With that, I'd like to close the SEDTalks Changemaker Showcase event and welcome you all to a networking cocktail in the reception hall just next door. Thank you.